everyone. My name is Bonnie. I am a researcher at Google DeepMind. And today I'm excited to talk about the paper, The Art of Scaling Reinforcement Learning Compute for LLMs. So we know that RL training has become the new scaling frontier. We know pre-training teaches the model about how the world works, but RL really unlocks the capabilities that matters the most. That includes test-time thinking, agentic capabilities, and things like scientific discovery. So the scaling laws for pre-training is understood pretty well. We know that there's this power law where the loss basically decreases log linearly with respect to the amount of compute. But what about scaling RL training? So far that's been pretty vibe-based. There are so many algorithms, many design choices, and not a quite scaling framework yet. So can we bring the same scaling framework? So in this paper, they found a scaling curve for RL training. So basically, RL training follows this like sigmoid scaling curve, where so the x-axis is compute, and the y-axis is the expected reward for your RL setup. And they found that you can basically fit the sigmoid curve during training. That's defined by the asymptotic ceiling, the compute efficiency, and the inflection point. So we have the asymptotic ceiling, which basically dictates how high your reward can go. So this is already different from pre-training. In pre-training, your loss always decrease, but in RL, you're actually bounded by how far your curve can go. And you also have compute efficiency, which dictates how steep your learning curve is. So what this also means is, if you look at this graph, if you stop the training too early, your results could actually be really misleading, because you could have some curves that starts really slow in the beginning, but take off very drastically later. So we see that RL training is very different from pre-training. It follows the sigmoid curve that's defined by this A, that's asymptotic ceiling, and B, the compute efficiency. So with different RL recipes, you hit pretty different ceilings. So they looked at different RL recipes like ScaleRL, QN, DeepSeek, and you see like pretty different training curves, which is really interesting. So this tells us that these algorithmic choices fundamentally limits what you can achieve, and you can't just train longer to fix a bad recipe. So it's very important to have the right recipe. So how can we build the best ScaleRL recipe? So this is the complete ScaleRL recipe that the paper came up with, and we'll go into each of the components a little bit. So there are a lot of design choices, and each of these design choices actually affects different aspects of scaling. So we have things like the loss function and the train-inference discrepancy. So these actually limits how high the ceiling, like how high your curve can go. So this is really important because you definitely want your curve to go as high as possible. There are also things like off-policyness and normalization, adaptive sampling that usually affects the efficiency of your training. So I'll go into off-policyness first, which is a pretty big problem in large-scale RL. So why do we do off-policy RL? That's because on-policy RL is very inefficient. What does on-policy RL mean? It's very simple. So you run your generate. So you generate a bunch of samples. You get your rollouts, and then you run a training step. And then with your new weights, you run a new step of generate to get the samples, and then you run training again. And you see that while you're running generate, some of these samples go really long. So for large amounts of time, your GPUs are basically just sitting idle. So this is a very big problem. Your GPUs are basically idle, like for large % of the time. So what can we do to fix that? So one way is to do async RL. So we basically overlap generate and training. So we run a step of generate, we get a bunch of samples. We use those samples to do training, but at the same time, we run generate at the same time. So we're always running generating and training at the same time. We're overlapping the two. But the problem with this is that when you're running training, the data you're training on could be generated by weights from a few steps ago. So your data is from a different set of weights than the weights you're training on. So this means that async RL is off policy. So the data generating policy, the data generating weights, is old compared to the training policy, compared to the set of weights you're training. There's also PipelineRL, which takes it even a step further. So in PipelineRL, we do these like in-flight weight updates. So as you're generating a trajectory, so for agentic tasks, these trajectories can get really long. We basically say, if we're generating a trajectory and midway during the trajectory, our new set of weights is ready, we just like swap in a new set of weights midway, and then we continue the trajectory from there. So you could have samples that are generated by different set of weights, which is pretty cool. And we can look at how PipelineRL compare with like off policy, and we see that PipelineRL is generally a bit more efficient, but all of them converges to about the same ceiling. There's also a very important parameter in PipelineRL, which is how how old are the data that you are willing to train on. So 8 here would just mean like you're still training, you could be training on data generated from weights 8 steps ago. So we see that a value of like 4 and 8 are usually fine. But then once you get to something like 12, the difference is too big, then like the algorithm just starts plateau and doesn't work anymore. So this is something you have to be very careful of. Okay, so that's more on the infra side, how we handle off policy on the infra side. What about on the algorithm and loss side? So how do we handle off policy on the loss side is we do something called importance sampling. So let's just ignore this term for now. So the term here, this is basically policy gradient. So that's the loss function for RL. But the problem with this term here is you have the learner and the sampler, which are different. Your sampler is usually a bit older than the learner. So here we basically add a different term. We add this ratio to correct for this mismatch. So we basically add this term that's basically the probability from the learner divided by the probability from the sampler to correct for this distribution mismatch. So there's a lot of math you can do on how you exactly handle this. So there's the very popular GRPO. So how they handle this ratio is they clip this ratio. So ideally we want this ratio to be about 1 because ideally like the sampling policy and the training policy are like pretty close to each other. So we want it to be around 1, but sometimes it can get a bit too all over the place. So in GRPO, they basically clip this ratio to 1 minus epsilon to between 1 minus epsilon and 1 plus epsilon. And then, so there's also DAPO, which is this very popular algorithm from ByteDance. So what they realize is with GRPO, your policy entropy actually quickly collapses because the clipping is restricting the trust region, but it also restricts, like the upper clip is restricting how much your policy is, how much exploration your policy is doing. So they come up with a strategy called clip higher. It literally just means clipping higher. So on when you do the clipping, so on the upper end, you just set a higher epsilon. So you have this like asymmetric clipping. There's also GSPO. So they do like sequence level importance sampling. So instead of running this importance sampling term on the token level, we can do it on the entire sequence as well. And then there's CISPO. Yeah, there are many variations. So previously, we were like clipping these token updates, which means we're basically dropping tokens where the ratio is too off. So here they say we don't really want to drop tokens. Can we just clip? So they came up with this trick to basically clip the importance sampling weight directly to stabilize training. And we can see how different loss functions affects the different asymptotic ceiling. So in this setup, CISPO and GSPO worked pretty well. You see the curve like working out pretty well. But in this case, like DAPO actually plateaued very quickly. So for different domains, you really want to get the algorithm right. Otherwise you just cannot get a good enough reward. Okay, and now I want to get into one of the biggest challenge actually in large-scale RL is train-inference discrepancy in RL. So it's a bit of a weird issue. Basically, your training stack and inference stack are optimized for completely different things. So these result in a lot of inherent mismatch just due to different kernels, precisions. So in training, you're using things like VLLM. For inference, you're probably using like Megatron. So what this means is even for the exact same weight, you can get very different result from the training stack and the inference stack. So this plot here, we see, so we have the exact same weight, exact same data point, and we get the probability from the training stack and the inference stack. And they should be the same. So if they're the same, they should line around the red line. But we see that in reality, they actually really scatters around the red line. So sometimes they're actually like really different from each other, despite like this is just like running the exact same way, exact same data. So this is actually a very big issue in RL. So there's this Chinese paper. So in their case, originally their algorithm, it's not working at all. So if you look at the gray curve over there, like it's just not learning at all. And then they realized, oh, we have this pretty big train-inference discrepancy across different layers and different components. So they went into it and fixed it one by one. So first they fixed KV cache. There's some precision mismatch. And just by fixing that, you get the brown curve. So just by fixing that, your algorithm just started working. And then they fixed like more like normalization, attention, and rope. And then you just see like the more like just fixing them one by one, the algorithm just works better and better. And at the end, you get the red curve, which is like pretty stable RL training. So in the ScaleRL paper, they do something similar. So they use this fix that basically casts these matrix multiplication to like FP32 for both training and inference. So you see that just with this trick, before this trick, we have very scattered values. But then after it, it's much more centered around the values are much more centered and aligned. And just by this precision fix, you can look at the curve over there. They got like a plus 17% relative ceiling. So just by fixing precision, you can affect your training performance quite a lot. This is also really dangerous because if you look at the orange curve, like there's nothing wrong. Like it's not clear like what is wrong. So these discrepancies, they're not obvious errors. They're just like silently corrupting your performance. So you really want to be minimizing your discrepancy for stable RL training. What else do we do in RL training? Another thing we do is adaptive sampling. So there's this trick called zero-variance filtering. It's really simple. It basically says, well, a bunch of problems, some of them are too hard, some of them are too easy. If they're too easy, the model always gets like a reward of 1 or always gets really high reward. If they're too hard, the model always gets like a reward of 0. So we just like skip these samples. We just like throw them away during training. And we only focus on training on data points where the model sometimes can solve it, sometimes cannot. So this really focuses the training compute on the learning frontier. There's also no positive resampling. It's also pretty simple. We say that as training progresses, the model starts to like master some problems. So some of these, they still pass the zero variance test, but they still contribute like very diminishing learning returns. So in no positive resampling, we say we track the historical pass rate per prompt. If the model can solve this problem more than 90% of the time, we just throw it away. And so this allows us to progressively focus on harder problems. What this looks like in the training progression is you might start with like 5,000 problems. The model will learn to solve like maybe 200 of them, and then we just drop those. And so gradually, we just have less and less problems to train on, and we focus only on the problems that are genuinely really challenging. And so the compute is never wasted on problems that the model already mastered. And we see that with adaptive sampling, this really improves compute efficiency just with like these two very simple tricks. And sometimes they also improve the ceiling as well, which is pretty cool. So we talked about the ScaleRL recipe. So we talked about different loss functions like grpo, dapo, and syspo, and also the train-inference discrepancy. So these two, they really affect the ceiling and just like how high your performance can get. And then we also talk about off-policiness and adaptive sampling, which really affects your efficiency, like how quickly your model is learning on the problems. So that was a very information-dense technical talk. What did we learn? So we learned that RL training follows these sigmoid scaling patterns. So that's different from the power laws. We learned that different recipes have different performance ceilings. And we can predict large-scale performance from small-scale training runs. We also talked a lot about different trade-offs like off-policiness, adaptive sampling, and different RL algorithm. They also affect scaling in different ways, some affecting the efficiency, some affecting the ceiling. So I hope you gain some insights for your next RL training runs.
Hi, how generalizable is this recipe across different domain of problems?
I think it's pretty generalizable. I think it's a very systematic way to think about RL scaling. So I think it's pretty generalizable, and it's probably a really good starting point. I imagine if you have super specific problems, you might like alter things a little bit, but it's usually like I think it's pretty generalizable. Yeah.
Yeah, I was wondering why do you think the shape is a sigmoid shape? And that's my first question. And second question is like, is there any fundamental limit to how high the ceiling can be?
Yeah, that's a good question. I think because RL is so different. RL is very different from deep learning in that deep learning you're training on a fixed data set. In RL, your model is generating the data that you're training on. So I think once your model is getting to a good enough point, then you suddenly get a lot of like very valuable learning points. So it takes off very quickly. So that would be my guess as to why it's a sigmoid shape. And as for the ceiling, there are definitely like fundamental limits. Things we talked about here include like the algorithm you're using, and also just like the train-inference discrepancy. If you have too big of a discrepancy, it just doesn't work that well anymore. I think those are like some limits on the algorithms. Yeah, on the algorithm side.
How much of it is related to like the base model big knowing? It's like to like a really shitty base model feels like very high.
Yeah, I think the base model capability, I think it affects both. So like with a strong base model, maybe you can improve really quickly. But for like worst-based model, like it takes a while. So I think it affects both. It's actually not super. Yeah, it's actually not super clear to me like how much it affects the ceiling, because like I think some small models are actually really capable, like if you just train it long enough. Yeah.
Is that have you done the experiment?
I guess not as much in this paper, but I think yeah, you see things like Cursor with like Composer 2.5, just with like even if you don't have the biggest model, like if you train it long enough on like high quality enough data, like you can get pretty far. So yeah.
I think on the previous question, one of the reasons why it's sigmoid is that the RL reward function is a finite domain, right? So eventually you'll hit a series. But if you do a dynamic, then it's a different thing, which brings me to my question actually. So it's wonderful that like we can predict, right? So and then we can, from a small scale, we can find out where it's going. But I wonder where the trade-off is on the innovation of it, or if it whether we know it phases out or not. And the reason why I'm asking is that like if you assume original neural network paper from 1958, right? With the limited compute, I'm pretty sure they hit a ceiling very, very quickly. They figured, okay, we cannot improve over this.
Yeah.
But like, I mean, assuming here, for instance, 100,000 GPU hours, we hit a ceiling and we cannot improve over that. But we don't actually know if 10 million hours will do it or not.
Yeah.
If we actually fix ourselves onto a recipe-based machine learning approach, and I wonder how much of it is a trade-off on we're actually giving up on some of the innovations that might actually pan out. Like for instance, the adaptive sampling, right?
Yeah.
So it's a fantastic method.
Yeah.
But like say it starts lowering the samples on once it achieves a certain task at say 90%, 95% accuracy.
Yeah.
There might be that one or two very, very rare cases that might actually save a life. That like we might not be sampling that because we think that you're already very, very good at that particular task, and then downsampling. So I want to get your opinion. Sorry, this one ended up being too long of a question, but where do you see the trade-off of like say how predictable is good versus like how much of an innovation space there is?
Yeah, that's a really good question. I think things are generally pretty predictable. Like if you just look at the learning curves, like once you get to a certain point, like you are not going to get much further than that. On the innovation side, yeah, I think like this is still very early work in like systematically thinking about these kind of things. So yeah, I think everything on the RL side is extremely early. There's like so much room for scaling. Like we haven't even talked about scaling like scaling the number of environments, scaling the number of domains. Like there's just so much you can do there. So I think yeah, people should definitely work on different innovations. And like the adaptive sampling, I think it's like very simple tricks people came up with. But yeah, I think people should definitely continue to work on innovations. Yes.
So you pop up adaptive sampling where we basically say type on those questions that we thought that the model is good enough to solve.
Yeah.
But is it possible that, after discarding those quote-unquote easy questions, the model will probably gradually lean towards techniques or skills that are more tailored towards the so-called hard questions.
Yeah.
And in return, results in a regression of those quote-unquote single questions. Was there a risk of this happen?
Yeah, that's a really good question. I think it's not super well studied. I actually think some of the adaptive sampling things, it's not very principled because it does change your training distribution in like unexpected ways. So yeah, no, I think people should study that more. And I do think it changes behaviors in like very unexpected ways. Like sometimes like your model could just like, if you overtrain it on like very specific type of problems, like you get very, very strange behaviors from those type of things. So yeah, so I think people should be very, very careful about that.
I know that most of media algorithms are like outcome-based rewards. Have we studied any ceiling for process-based rewards, or do we have any scaling for that?
Yeah, so I think for a lot of domains, like people are using like reward models or rubrics. So I think all these like scaling laws, they still pretty much hold. Maybe with some reward hacking, but it still pretty much holds. With process rewards, I'm not quite sure actually. I don't. Yeah.
Traditional RL has a lot of reward shipping.
Yeah.
So they do a lot of reward shipping.
Yeah.
In most of these cases, it's just like a binary reorder and Messiah.
Yeah.
Do you believe that the similar ceiling holds for process-based rewards that rewards are more finely?
Yeah, I think I'm seeing like very simplified settings of process rewards where you do get like different partial rewards like per step and you sum over that. So I think in those cases it still holds. But for if you're getting to like more nuanced cases of the, like different process, like very rewarding very specific parts of the process, yeah, I'm not too sure. I'm not too sure what happens there. Yeah, I think it probably looks something different. Yeah. Over there, yeah.
Yeah, this was really interesting. It got me thinking more from a product perspective. I'm wondering if it makes sense to start labeling models that we push out and deliver from like this predictive metric, right? Like, would it make sense to have that label as a marker for this is where we think the model is and its potential, or there's
Yeah, I think that would be really useful. It's actually, yeah, it's like really hard to assess like the potential of the models. Like even for the open source Chinese ones, like you can get like very surprising results from different just by post training it. So I think, yeah, I think that certainly could be really interesting.
Because on the flip side, I'm thinking that could be useful, but also is that so much like insider baseball, like I'm just a product company, is that, or do you think that would be useful for just like open science or?
I think that could be useful for open science for sure. I think it would be very interesting. Yeah, I'm not sure if how the economic incentives align on that front. But yeah, I think it's definitely like very interesting research. Cool.
All right,
Yeah.
thank you, Bob.
Thank you so much.